Thank you everybody. Today we're going to be looking at some more of physics. Now the last one wasn't too in-depth and it didn't have too many explanations. So for the physics newbies out there, this lecture is just for you. So you can really understand some relativity. So it really just digs down to the basics. So first of all, if you're a basic physicist, you should probably accept the equation work equal force times distance is a fact. But you may have wondered, why do we just rotely memorize these? Why can't we understand the meaning of these? Hold it. Now, well, the meaning of this is that the distance. You'll see. The meaning of this is that the work exerted is by the force you're exerting over an object that's pushing it a certain distance. How much energy you let off while pushing an object with a certain force over a certain distance. So now, this is the basic definition. But let's also describe the units of work. The units of work is joules. However, this isn't so specific. Yes, it was invented by this dude, Charles Joule, but that's not what we're going to talk about. What does joule actually mean in fundamental units? Well, it gives us a joule is actually made of Newton times meters. Do not confuse with the impulse. Oh yeah, maybe I should differentiate between them since they're confusing. Don't confuse this with the impulsive unit, Newton seconds. So now, Newton meters, and then the Newton is actually equal to a kilogram meter second squared. Because a Newton is equal to, I think, mass, kilo times some acceleration, which is meter per second squared. So now a meter is just a meter. It's fundamental. That gives us a joule. A joule is actually a kilogram meter squared over a second squared, which makes sense. So now that we have that done, we're going to talk about how we can define the relative definition of kinetic energy. Well, I want to talk about graphs for a second. Oh, wow. Okay. So W equals D. So let's say that we have a sort of graph here with D for the x-axis. Maybe I should make this more straight. And F for the y-axis. Well, now let's make a little weird. The function. So now you may have heard this quote in calculus: the area under the curve. This is called the integral. And now the area of this is equal to the dot product of force times distance in this case, since we can't just use the regular area for this kind of curvy monstrosity. So this is the dot product of the vector's force and displacement. That gives us something equal to work. Now this work is made by the integral, which is found by summing up the area under the curve. Sometimes, when a shape is geometrically perfect, you might want to use something called the Riemann sum, which it looks a little bit like this. But we've talked about that in one of the first lectures, I think 1, 2, 3, or 4, looking back at my lesson notes. So I think you should know that if you started watching the first few lectures, physics 1, 2, 3, 4, etc. So now this integral is going to look like this. However, we're integrating over some sort of distance. We're pushing an object over some sort of distance. So we're going to differentiate over that distance. That's what we call the differentiator, or whatever. And then we call this the integram, because that's what we're taking the integral of. Now, due to the work energy theorem, we know that work equals to kinetic energy. Now, I want to go really in depth, so I can't. I'm not sure if I can do this, but huzzah! Let's try to reprove the work energy theorem. I have no idea what I'm doing, honestly. So, anyways, work is equal to force times distance. And then we're assuming that's equal to, we want to know if that's equal to kinetic energy, half mv squared. Well, let's do this like a proof by contradiction. So now, F is equal to MAD, equals to half mv squared. So, if this simplifies to something similar, then half v squared equals to AD. Oh my god. It's beautiful. It's beautiful. It's one of the basic equations, and I love it. So, now, this is one of the regular physical equations, which is obvious if you want to know something. Now, this sort of proves the work energy theorem if you know the basic equations of physics. So we don't have much time for the sake of it. So that means that work is actually the change in kinetic energy, which gives us force dt. Oh yeah, did I forget? I did this a little bit wrong. We actually have to take the dot product of these two, since they're both vectors. dx is just another way to say the derivative of d. That d thing, that x thing did not stand for derivative. This d thing does. Derivative also means basically change of, or delta in a sense. So, yeah. So, this x actually represents mu d. We just don't represent them with the same symbol so we don't get confused. So that gives us f times dx. Well, this is a helpful thing. F equal p over t. Want me to prove it? Here. Well, j is actually equal to p because ft is actually equal to mat. MAT is actually equal to V if you pay attention, and MV is equal to P. So that's how to prove that P is equal to J, which is what we started with over here. So now that means that J is equal to P. Now, if we solve for force in the J equal Ft equation, we get F equal J over T. Now, we know that P equals J, so we can substitute J for P. Trust me, this will help us later, because it contains V. Meanwhile, J only contains Ft over T, which will just bring us back to the beginning. So trust me, that'll help a lot. So that gives us Ke equals to, oh yeah, we're integrating over distance. This arbitrary distance we'll call delta x over xi to xf. So F is equal to dp, change in momentum, over dt, change in time, times dx. Now, you should know that delta x over delta t or dx over dt is equal to velocity. No d, because a change in velocity or dv would actually be acceleration. So that gives us xf dp times dx or times 1 over dt. Now, some basic algebra will rearrange this to become dp times dx over dt, which simplifies to dp times v. The next part will be coming soon. With that, I'm going to tune out for today. Thank you everybody for watching, and see you later. Oh yeah, I forgot. I don't want to end the live yet because I didn't actually cover how we did this. I didn't actually cover how we did
finished that.